Okay, I guess we'll get started. Hello, everyone. I'm Herbert Winful, a professor in electrical engineering. And today I'm delighted to introduce Professor Adrienne Stiff Roberts. She's the Jeffrey N. Vinnick Professor of Electrical and Computer Engineering at Duke University. She's going to be this year's Willie Hobbs Distinguished Alumni Lecturer for our department. Now, the seminar series named after Willie Hobbs Moore, who was the first African-American woman to earn a bachelor's and a master's degree in electrical engineering from Michigan. And she was also the first African-American woman to gain a PhD in physics in the US. She then went on and spent several years as a research scientist at Ford. And so we named this lecture series after her. And we bring in distinguished alumni who can serve as role models for our students. And so today we're delighted to have Professor Adrienne Stiff Roberts. She earned a bachelor's from Spelman College in 1999, and also a bachelor's in electrical engineering from Georgia Tech. Then she got a master's in electrical engineering from Michigan, as well as a PhD in applied physics. She did her research with Professor Bhattacharya. Professor Stiff Roberts has won several awards, including the NSF Career Award, the Presidential Early Career Award for Scientists and Engineers, and the IEEE Early Career Award in Nanotechnology. So I'm pleased to have Professor Adrienne Stiff Roberts with us today.
Okay, well, thank you,
please,
Professor Winful.
just before she starts, could people turn off their microphones so that we don't have feedback? And then at the end, there'll be time for questions, and questions can be sent to the chat box, which is up on the right of your screen. Okay.
Yes, thank you. So first off, I'm sorry that I couldn't be there in person to deliver the lecture. And I understand that you all are dealing with classes being canceled as well. So we're all doing the best we can with the remote delivery of this lecture. So I appreciate Professor Winful and Ann Stahl's efforts to still make this happen. This talk is really just sort of reflecting on my development as a professor in my career. And so we can go ahead and get started. So I'll be talking about my research program, which is in resonant infrared matrix-assisted pulse laser evaporation, and my attempts to use this to enable hybrid thin films for optoelectronics. But really, it'll be more so just a talk about what I do and how I got there. It is targeted towards students, so just keep that in mind. So academia, that's about research, teaching, and service. That's what we all sort of know, although for myself, when I started to learn that I wanted to be a professor, I thought that that was just about teaching. I didn't know anything about the research or service parts of being a professor. I thought you taught classes. But of course, once I entered the profession, I learned that there's a lot more than just teaching. There's the research and service parts, but really some of the things that are most exciting are what lie at the interface of those areas. So if you look at this diagram, you can sort of think about the intersection of research and teaching is mentorship, mentorship of our students, especially graduate students. At the interface between research and service, you have thought leadership, trying to determine what are the exciting areas to look into and to pursue, and where you're going to spend your efforts because of the scientific interest that lies there. And then between teaching and service, you can think about having outreach. So outreach to your community, outreach to professional organizations, but something that you're contributing to society beyond just your own research program. And so it's really those areas of interface where I get most excited about being a professor and being in academia and the ability to contribute to society at large. So I started my education at Spelman College in Atlanta, Georgia, and I got a dual degree with Georgia Tech. So that means I got 2 undergraduate degrees, one in physics and one in electrical engineering. Spelman College, of course, is an HBCU for women. And then Georgia Tech is an engineering-specific school. So they are 2 very different institutions, and I had very different experiences at each, all of which, though, really helped prepare me for eventually what I started to do. So as I said, I didn't know a lot about research or what that meant or what that involved. My first research experiences were at the NASA Ames Research Center in California. So at Spelman, I had a fellowship, it was Women in Science and Engineering, and this fellowship was a full ride, a scholarship was a full ride to go to college for both the Spelman and the Georgia Tech parts, and we spent summers at Ames Research Center to do research. So my first research experience was basically graphing data using Excel, and through that, I was working in a lab on psychophysiology. So the idea here was that an astronaut would wear a suit, it would have sensors integrated into the suit, and these sensors would provide feedback to the astronaut so that hopefully they could control their body temperature or their pulse or their heart rate, you know, these different things, and prevent themselves from getting sick. So Mae Jemison did participate in that study. And so I graphed a lot of data for subject 8. And so I just like to think that Mae Jemison was subject 8. I don't know if that's the case, but that's what I'm going to go with. So I think one big lesson I learned there was just that, you know, especially as a student, as a young person, your research experiences that you have at first are not always the most exciting. Because graphing charts with Excel wasn't the most exciting thing, but I still learned something. I learned how to use Excel very well, which did serve me well throughout my PhD. And, you know, engaging in research is often about just making the best of whatever situation you're presented with. My second summer that I spent at Ames Research Center was a little bit more interesting for me. So in this case, I was working on a system to measure the amount of food that mice ate when they were on an mission in space, and they were studying mice. They wanted to keep track of how much food they were eating. So the system that I had to develop was basically having the food, which is like a peanut butter bar sort of on a plate, and you strike the plate so that it vibrates, and then use an accelerometer circuit to measure the frequency of the vibration and then determine how much mass of the food was on the plate and therefore how much had been eaten by the mice. So this is really interesting, but it was very challenging for me because I had to build this circuit. Now, I had studied physics, I had studied circuit elements, I had seen a circuit diagram, I had never built a circuit, I had never touched a soldering iron. This is before I was at Georgia Tech, so I hadn't done anything like that, and I had to build this circuit. So it was a challenge for me, but you know, I worked hard. You can see this is an old Polaroid that I was actually able to save of me sitting next to the system that I built, and I have a big old smile, so I was happy with what I was able to do. And again, first real experience of being presented with something that I didn't know how to do, having to figure it out, you know, having to deal with the troubleshooting that came up, having to get help from others, and then being able to have a successful result. And so that, of course, is what research is about to a large extent. So for graduate school, I went to University of Michigan, of course. So I entered into the applied physics program. So I got my PhD in applied physics, and then I took some additional classes so that I could get my master's degree in electrical engineering. And I ended up doing my research with Professor Bhattacharya in the ECE department at Michigan. So Michigan was really a great experience for me. I'm from North Carolina originally. I went to undergraduate in schools in the South. So coming up to Ann Arbor was a big change. One of the strongest memories I have is that first big snow that happened in Michigan, and I was in my apartment looking out the window, and I was watching television waiting for when they were going to cancel classes, and it never happened. And then I realized I've got to get up and go out to this or I'm going to be late for class. So that was a big change for me. But the other thing about Michigan that was really great, especially with the applied physics program, is that from day one, I felt welcomed, and I felt like I had a support system, and that there were people there at Michigan that wanted me to succeed, and they were going to help me succeed. And of course, that's extremely important when you're trying to do a PhD. And so That's something I really value about my time at Michigan, and that was from everyone in the applied physics program through to my PhD advisor and the faculty that I interacted with. So my project was on making infrared cameras work at higher temperatures. So you can have infrared cameras that are based on thermal technology, but they don't give you spectral resolution to give you better quality images. If you want to have infrared cameras that are based on photodetectors, where you're actually detecting infrared photons, then that becomes more challenging because they operate at higher temperatures. That means you have to cool down the system to work at liquid nitrogen temperatures in order to be able to detect those infrared photons. So this is showing a picture of me in the infrared, and you can see that there are many tiny black spots that are present. Those are pixels that aren't working. And from this infrared image, that's still having an operability of pixels on the order of 98% or so. So the challenge of getting high quality images in the infrared is a big one, because even when you have 98% of your pixels working properly, you can have your image be severely impacted by that. So yes, my work was then doing molecular beam epitaxy with Professor Bhattacharya to grow quantum dots that would be used to make these infrared photodetectors and hopefully allow them to operate at higher temperatures because of the unique properties of these quantum systems. And one thing I should mention about how I began working with Professor Bhattacharya is that in undergrad, I struggled a lot with quantum mechanics. It was a really difficult subject for me. I did not perform well on the physics GRE because of the quantum mechanics part. And so when I came to Michigan, that is some of the most focused and intense work I've put in, was to do well in that quantum mechanics course that I took in the physics department with Professor Berman, and really had to be on top of my game. And again, working with other students struggling to try to understand this information. And while in the applied physics program, when professors would come to tell us about the different things they were working on, Professor Bhattacharya came in and started talking about lasers and how he was making them with quantum dots. And I was immediately fascinated, because this subject that I worked so hard to try to understand, there was like a real life example of that particle in a box problem being used to make actual devices that were useful. And I found that fascinating. And so I decided to join his group and to work in that area. So this is a picture of several members from Professor Bhattacharya's group. I was not able to find a digital copy of an older picture when I was actually in his group. So this was taken from 2015. I believe we're at an STIE meeting. So several former members of his group were there. We got together for dinner. Professor Bhattacharya is seated here. And so just had a nice dinner and time to catch up. And I suppose one thing I want to mention with showing this picture is just that, again, that very positive experience I had being in the research group, working with others, being exposed to lots of different types of people and projects, and having a really good camaraderie among the group members. All that really contributed to having a positive experience. But I was able to find a picture of the graduating class from the applied physics program that I'd like to share. So I was able to find this picture. So I can't hear any laughter, but I'm going to assume that everyone's laughing a lot because of the graduating class picture that I have here from Michigan. But I suppose the point of showing this is that I've always been a huge nerd, love Star Trek, Doctor Who, and other things, and really that's a big part of why I decided to go into science in the first place. So when I think back on my graduate education, I would say there's some important things that I learned. I'm showing a picture here of me with my parents. And I want to show that because in terms of deciding what I wanted to do as a career and becoming a professor, it was never really a huge leap for me, because I was very fortunate to be exposed to that idea because of the trajectory of my parents. So my father's a professor in math education at North Carolina State. My mother was a librarian at North Carolina Central. So they had both gone to college. They came from North Carolina. They attended segregated schools. They both went to college at predominantly white institutions where they had to deal with being minorities and existing in that space. And so I had a lot of support even from my family in terms of how to navigate those spaces and how to stay focused and how to be successful. And even with all of that support, I still had a lot to learn and I still made a lot of mistakes. And so certainly for the students, I think it's important to share what some of those lessons were and what some of those mistakes are that I made. One important lesson that I learned in graduate school is that anyone can be an advocate or a mentor. And so you have to be willing to expand your network so that you can meet those people that will be helpful to you. And you can't always tell right away who those people might be. So you have to be willing to engage and to talk to people and to meet others. In terms of being a student in a research group, I'd say one of the biggest things I learned is that if you do what it is you say you're going to do, you're usually ahead of the game when it comes to interacting with your advisor and also just working in a group. Just doing what you said you're going to do is always beneficial and useful. Another thing that's important that I learned is that you have to learn how to say no, and that really comes into play as a faculty member. You have to set priorities for what your goals are and what the activities are that are going to be most beneficial and most useful for you to accomplish those goals. And sometimes that means you have to say no, and that's a skill that you have to practice and learn how to do. And I guess the other lesson that I learned is that the PhD is a long game. It's going to be frustrating. There will be challenges. You will make mistakes. But the important thing is to be able to try again and to be willing to adapt. And once you finish, then you're finished, and it doesn't really matter how bumpy that road was once you get to the end. And so that's an important thing to remember as you're dealing with difficult times and wanting to stay focused on moving forward. So some mistakes that I made in graduate school that I want to share just to encourage students to not repeat those mistakes. So one is that I did not really develop strategic relationships with all of my classmates and contemporaries. I certainly developed those relationships with the people in my group, but extending beyond that as much as I should have is not something that I did. And that's important because these are going to be the same people that you continue to interact with and run into throughout your career. And so it's important to develop those relationships, to take time to nurture those relationships and to keep them in place. So that's one thing that I learned. Another thing that I learned is that I was very dedicated and worked in the lab a lot to the detriment of participating in other types of activities. And that's good for finishing the PhD and being very productive and getting all of your work done. But at the same time, graduate school, as hectic as it is still one of the last times you have some flexibility in terms of what you want to do, especially if you're going into an academic career. So it is important to take time to smell the roses and to try to get that work-life balance even in graduate school. So to switch gears, I just want to share some about what I do for my research, about what my research area is. I work with semiconductor materials for optoelectronics, and as I mentioned, that was started in the context of these indium arsenide, gallium arsenide quantum dots. So just as a quick review, in case there are any undergraduates on the line, right, you have a single crystal of silicon, which is a semiconductor device, and what's special and nice about it is that you have this very periodic arrangement of atoms that are in a lattice, in a crystal lattice, and because of quantum mechanics, when these atoms interact with one another, the energy level for the valence electrons as they interact with nearby atoms, these discrete energy states will split into as many states as there are atoms coupled together or nearby. And so that leads to this creation of a band structure in a semiconductor. We've got a conduction band and a valence band separated by a band gap. And that's important for optoelectronic devices because with the presence of this band gap that has an energy difference comparable to the UV visible near infrared range, you can control the creation of electrons and holes by shining light, for example. So you have an incident. So in this case, if you have if you have an incident photon on the right, you can excite an electron and leave behind a hole, and that's the sort of function that would happen to create a photodetector. And on the left, if you have excited electrons that recombine with a hole, it can release a photon, and that's the sort of function that would be related to a light-emitting diode. And so having the presence of this band structure allows you to make optoelectronic devices that are based on the interaction of light and matter. And so a lot of the devices that I've worked with have been light-emitting diodes, photodiodes, or photodetectors, things that detect light, like the infrared photodetectors I mentioned earlier, and then also solar cells, which are basically detectors, but they're working without any bias being applied, any voltage being applied. And when you shine light on this device, it can generate power and provide power to drive a load. So So looking at the materials that can be used to make these different types of optoelectronic devices and trying to control the material properties when we deposit them as thin films. And so that's what I started doing at Michigan. So this is a picture of the molecular beam epitaxy machine that I used when I was working in Professor Bhattacharya's group at UMich. It was a giant machine. I didn't know anything about MBE before I started my PhD. I learned all of it while I was a student. And it's a massive undertaking, but it allows you to make really cool structures like these quantum dots. So these are cross-sectional transmission electron microscope images of quantum dots that I drew using that molecular beam epitaxy machine. And you can see the size scale for these images. So these are nanometer-sized structures, and they have complex shapes. You know, this is like a pyramidal shape that's present, or perhaps a lens shape. And trying to control these quantum dots is a challenge. So there are a lot of advantages expected for quantum dot infrared photodetectors because of the nanoscale size of these quantum dots. And we did demonstrate many of those advantages during my PhD and with working in Professor Bhattacharya's group. But a big challenge that always remained is the fact that this process, this growth process by MBE, gave you an ensemble of quantum dots that had non-uniform sizes. And because you had this size distribution, this inhomogeneity within the sizes of the quantum dots, it was difficult to control properties in a device which is on a larger scale than just a single quantum dot. So when I started at Duke with this sort of challenge in the back of my mind, I became interested in colloidal quantum dots. So colloidal quantum dots are dots that you can synthesize by chemistry in a beaker. And in this case, you have the same material system for the quantum dot, let's say cadmium selenide quantum dot, and you change the size of the dot by controlling the chemical process that you follow for the synthesis. You can control the size. And of course, because of quantum mechanics, we know that as you change the size of the particle, you change where that energy gap is between the ground and the first excited state. So you control that energy difference, which means you can control the wavelengths of light that are absorbed or emitted by that quantum dot. And so this is really cool when you think about semiconductors in general, because now, right, if you wanted to change the wavelength of light emitted or absorbed by a bulk semiconductor, you have to change the composition of that material. Here with these colloidal quantum dots, you change the size of the same material, and you can get a wide range in different colors. But the challenge became, how would I be able to make optoelectronic devices and films of these nanoparticles? And this is showing a scanning electron microscope image of these nanoparticles in a polymer. So a lot of the work, especially when I was starting my research program in 2004, these nanoparticles were embedded in polymer films. And so I wanted to figure out a way to make thin films of polymers with inorganic nanoparticles embedded in them. And that led me also then to learning more about polymers. So polymers, especially a specific class of polymers relevant to optoelectronic devices. So when you have these polymers, you have these monomer, right? This monomer is the base unit that's repeated n times to form a long molecular chain. And the double and single lines are representing double and single carbon bonds. And this is essentially a periodic pattern. You have alternating double, single carbon bonds along the backbone of this polymer chain. And that leads to delocalization of electrons, very similar to what happens in silicon. It's just not as well ordered and not over as large of a scale in distance. But because you have this repeat single, double carbon bond, you can introduce a band structure into a particular class of polymer materials, and these are known as conjugated polymers. And so these conjugated polymers then can be a matrix for the inorganic nanoparticles to try to make optoelectronic devices based on these quantum dots. So it was this interest in quantum dots and trying to have a better behaved quantum dot material system. One thing I didn't mention, because the colloidal quantum dots are spherical, so if you want to predict what the properties will be, it's a lot more straightforward to do that with a spherical quantum dot. So I was interested in this. And so why, if you can make devices out of these colloidal quantum dots in a polymer, things start to have the same types of optoelectronic devices I'd studied before, light emitting diodes, photodetectors, and solar cells, but they can be implemented in very different ways. And one obvious change is that if it's in a plastic, it can be flexible. So you can think about having flexible optoelectronic devices And they can be integrated into systems in very different ways. For example, they could be integrated into clothing, or there could be other things about them that you wouldn't be able to achieve in a system like silicon or gallium arsenide. And so this really drove my interest in these organic, meaning the polymer materials, and hybrid, where you have organic polymer materials with inorganic nanoparticles embedded systems. But I needed a way to deposit those. And so this is what I developed during the course of my research program at Duke. And it's a variation of pulsed laser deposition. So it's called emulsion-based resonant infrared matrix-assisted pulsed laser evaporation. And this is a picture of the system that I have at Duke. So this is I have the growth chamber and load lock chamber, and the laser is sitting in the black box. And this variation pulse laser deposition will allow the control and deposition of these hybrid materials in a way that's very difficult to achieve with other approaches. So this is showing the inside of the growth chamber. There's a target cup that sits here at the bottom, and it's actively cooled by liquid nitrogen so that the target solution can be frozen, and the substrate sits above the target cup. And this is a picture of that frozen target cup. It has actually two different solutions frozen inside, or emulsion. So just to explain a little bit more about what this process is and how it works. So as I said, it's a variation of pulse laser deposition. People have tried to do pulse laser deposition of polymers. So all of this is developed in the context of polymer thin film. Just to back up, people have certainly demonstrated thin film, vacuum-based physical vapor deposition of organic small molecules. People at Michigan have done that, Stephen Forrest. And that's very straightforward for small molecules because they are much more crystalline. They can be tightly packed and ordered because of their small size. They can be thermally evaporated without damaging that small organic molecule. And you can make very high performance devices. If you want to do the same thing with polymers, it becomes a lot more challenging. And that's because the polymers have a much larger molecular weight. They're much bigger. There's many more opportunities for that molecular weight to be damaged. And that's a problem if you want to make the optoelectronic devices that I'm talking about, because as I mentioned, the size of that backbone, that repeat unit of single and double carbon bonds, that's determining the extent of delocalization that you have in the electrons. So if you do anything to damage that molecular weight, you're making it difficult for the semiconductor properties to be realized, for that band gap to be realized over a large size. And so that's the challenge for trying to do physical vapor deposition of polymers. So people first started trying to do pulse laser deposition. So sort of the traditional approach where you had a solid target made up of polymer pellets or a powder, and you hit that solid target with a UV laser, a high energy ultraviolet laser. And the idea is that you would then sublimate, the target material, and then it could reconstitute on the substrate. The problem is that when you do this with polymers, you're not getting the polymer material that you synthesize. You're getting all types of different species, atomic species, diatomic, molecular, ionic, or other low mass species. It's not the polymer that you synthesize with the properties that you designed. So at the Naval Research Lab around 1999, people started working on and demonstrated ultraviolet MAPLE, matrix-assisted pulse laser evaporation. And for those that may be familiar, this is somewhat similar to the idea of MALDI. The idea here is that you take your polymer, you dissolve it in a solvent, and you create a solution. That solution is frozen, and the idea is that the solvent, which is the matrix, the solvent will absorb most of that laser energy, and it will sublimate. And then when it does that, it will release the polymer that's now protected from the high energy UV laser. That's the idea, but that's not actually what was observed, because with the UV laser, that polymer, whether the matrix is there or not, that polymer is still absorbing that ultraviolet energy. And so you still have degradation of the polymer molecular weight in particular that is a problem. So people then demonstrated resonant infrared matrix-assisted pulse laser evaporation. And in this case, you change from the UV laser to an infrared laser. So the first demonstrations used a free electron laser because it's a tunable laser. It can give you tunable wavelengths in the infrared. Problem with the free electron laser is that it's the size of a building. So it's not very practical for being able to use in a system. But the idea, though, is that you have this tunable infrared laser. You have your same polymer dissolved in a matrix, which is the solvent, and you can then tune the infrared laser to a vibrational mode of a bond that's present in either the solvent or the polymer if you wanted to. And you then have resonant absorption of this laser energy. And because it's an infrared laser that's much lower energy, you can protect the polymer material. So what we developed in my lab is emulsion-based resonant infrared matrix-assisted pulse laser evaporation, RIR-MAPLE. And that was really driven by the fact that we did not want to use a free electron laser. So instead, we used an erbium-YAG laser that has a peak wavelength at 2.94 microns. And that erbium-YAG laser, that energy is resonantly absorbed by the vibrational modes of hydroxyl bonds, the OH bonds. And so water has two OH bonds, and so water can resonantly absorb this laser energy very well. Now, most of these conjugated polymers that have those semiconducting properties will not dissolve in water. So they dissolve in nonpolar solvents. That means we had to develop a solution, a target solution that could resonantly absorb that laser energy, which is how we arrived at using emulsion. So our targets are frozen oil and water emulsions. But these aren't simple, just oil and water emulsions. They have 5 different components. You have the polymer that you want to deposit. You have the primary solvent, that primary nonpolar solvent that it wants to dissolve in. And then a secondary solvent that also has OH bonds, but is low vapor pressure so that the target doesn't just sublimate in the vacuum of the chamber throughout the growth. We use a continuous phase of water, and this is the matrix. This is what is resonantly absorbing the laser energy. Then we have a very small amount of surfactant to keep this emulsion together just long enough for us to flash freeze this target solution in our growth chamber. And so these are very complex emulsions. They're difficult to predict what the behavior will be, and so we spent a lot of time trying to understand that better. But MAPLE was really great then. This emulsion-based approach for RIR-MAPLE is great to achieve our goal, which is to be able to deposit materials, thin films that could enable optoelectronic devices of organic and hybrid materials, because for one thing, it enables heterostructure design. So things that are done all the time in a system like MBE, molecular beam epitaxy, but is extremely difficult to achieve when you move to polymer systems that are typically deposited using solutions. So one is just the ability to grow layered materials of layered films of different materials. So having one layer that's one material, a second layer that's a different material. And that's been a challenge for polymer films because they typically have the same solubility. So if you put down one layer and then go to the second layer, you'll destroy the layer underneath because they're soluble in the same solvent. But MAPLE, because of this process, is essentially a hybrid physical vapor deposition process, and it's essentially dry. So we significantly reduce the exposure of the film to solvent such that we can grow layered structures. Then the other thing that you do in inorganic systems like MBE all the time is to grow a film. The composition is determined by what you deliver to the film, and so then the function of the film is determined by the composition. That's difficult to control in a polymer-based system like the polymer with the inorganic nanoparticles, because when you blend those materials in solution, they want to segregate into different phases. They don't want to blend nicely. But MAPLE allows us, because of the process, to control the blending on the nanoscale because of the way the materials are delivered to the substrate. And so because of this, you can start to do heterostructure design in organic and hybrid materials using polymers that's not really possible in a lot of other techniques. And so when we think about the parameter space available to control this, the most important parameter is the target composition, the chemistry that's used to create this emulsion, but also the chamber pressure, the substrate temperature, the distance from the target to the substrate, and also the fluence or the power of the laser that's coming in. But this is just a schematic diagram that's showing the process that I mentioned. So we have this erbium-YAG laser, it's infrared, it goes through a rastering system. So we have the target that's cooled by liquid nitrogen, and this target cup is rotating, and as it rotates, the laser rasters back and forth so that you're getting coverage, a radiation of the laser across the entire target surface. And then per laser pulse, you're sublimating the matrix. And when it does that, you're transferring kinetic energy to these emulsified particles that are within the target. And they get released to form a plume, and they intersect with the substrate to deposit the film. And so a lot of our work has been understanding and describing and controlling this process. So we have been able to demonstrate some cool capabilities of MAPLE as a result of this technique. So here we're showing a distributed Bragg reflector, and this is actually work that I did with one of my former group mates in the Bhattacharya group at the University of Michigan. So here we're showing a distributed Bragg reflector, where Wei Dong, my collaborator, he designed a distributed Bragg reflector in the green. And it was based on these 16 repeat layers of 2 different polymers, P3HT and PMMA, and they had a particular thickness and a particular refractive index. And so if you had these stacked layers, because you're controlling the reflection and refraction at each interface, you can create a mirror. So the design was in green. We grew this by maple and went to measure the properties, and we got the red curve. So when we look at the red curve, the matching with the peaks with the green curve is not that good. So then went back to the simulation and took into account the surface roughness of these polymer films that are inherent to films deposited by maple. And when you account for this, 8 nanometer, 13 nanometer surface roughness in the design, we got the blue curve. And there you see much better matching between the peaks and the simulation and then what we measured. And so the point here is not that we made a good DBR, because the reflectance is only 60% when we were shooting for 100%, but it does have the behavior of a DBR, which means that with the maple process, we were able to control the film thickness and the interface quality well enough that the DBR function could be observed. And that's something that's extremely difficult to achieve in a solution-based process. Also, just a nice demonstration of the fact that this is really essentially a dry process, even though some solvent contamination of the substrate does happen. This is showing deposition of an inorganic part. So the first example was just a polymer. This is just a nanoparticle. These are actually silver nanocubes that have a side of about 80 nanometers, so relatively large nanoparticle, and showing that we can control the surface coverage of deposition by maple just by controlling the concentration of the solution or the time that we do the deposition. And this is showing that we deposited these silver nanoparticle films on a variety of substrates. And so the wetting properties would be very different on each of these films, on each of these substrates. And so if this were not a dry process, you wouldn't see this similar type of deposition regardless of the substrate. So this is nice evidence that we essentially have a dry process with this. And another demonstration that gets back to the goal of making hybrid materials is showing, in this case, inorganic nanoparticles embedded in a polymer, which is where I started, how I got into this area, because those are the types of films that I wanted to make. In this case, these materials weren't chosen for an infrared photodetector, but for solar cells, organic solar cells. And the thing that's interesting to note, again, evidence that with maple, you're able to supersede the impact of solvent, but rather have the blending and the morphology of the film be determined by the laser deposition process. So here, these are showing nanocomposites of these nanoparticles in a polymer, and they're being deposited here by spin casting using 3 different solvents. So as you can see, the morphology or the distribution of these nanoparticles within the polymer matrix varies as a function of the solvent that you use, just based on how that solvent evaporates. When you look at the same 3 solvent systems deposited using RIR-MAPLE, you get the same sort of random, homogeneously distributed nanocomposite of these nanoparticles in the polymer. And so while it's not an ordered film, it is homogeneous, and it's got blending of these 2 components on the nanoscale, which is something, again, that's difficult to achieve with the solution process. So, so I jumped the gun a bit, but I've got these inorganic, these hybrid materials, right? And the reason that's cool is you could eventually do something like vibranium, right? The reason vibranium is cool is because it can do all of these different functions at the same time. It can absorb energy, it can store energy, it can release that energy, it's very hard, right? So very different functions all in a single material. And if we wanted to try to accomplish something like that in real life, how would we do it? And one way that you could do something close to that would be to have hybrid materials. So taking properties from organic materials, properties from inorganic materials, and putting them together. So I looked at some of that with the nanocomposites, nanoparticles embedded in an organic matrix, but those are very challenging because in the images I just showed, it's a random distribution, sure, it's homogeneous, but it's not well ordered, it's not well placed, so it becomes very difficult to try to predict what material properties will be. And so this is what's really interesting about work I'm doing now related to hybrid perovskites. So hybrid perovskites have a lot of interest because they've demonstrated very high power conversion efficiencies as solar cells. But the thing that's really cool about the hybrid perovskites is that they're a hybrid material. So they have an inorganic framework made up of metal halides that are represented by these octahedra. And within the space of these corner-sharing octahedra, there is an organic molecule. And this is a crystalline structure. So you know exactly where all the different components are. You can predict what the properties will be, and you can control those properties, and you can have the structure, you know, the process structure property relationships that you need to really advance a particular technology. So a lot of the work that's been done with these perovskites have been these three-dimensional bulk perovskites, where you have a small organic molecule in this inorganic framework. And people make these materials very well with solution processes. You don't need maple to make these materials. Where maple comes in is there's a lot of effort to replace some of the small molecules with a larger organic molecule. And when you do that, you can start to really change the properties of the material. The smaller organic molecules just keep the structure together. They're inert. They're not really participating in the overall properties of the material. So if you go to larger organic molecules, you can introduce functional molecules, things like dye molecules that are actually participating in what the optoelectronic properties are of the material. And so you can introduce these organic materials, and they give you essentially what can be a self-assembled quantum well, sorry. So as you increase the amount of organic molecules that you have, you create these layers of inorganic layers. And so you have a self-assembled quantum well of the organic and inorganic layers. And you can eventually get down to a situation where you have a single inorganic layer and a single organic layer. And so that is where maple can come in, because those types of materials can be very difficult to synthesize by a solution process. So we did have to modify the target that we use in maple to make them applicable for the hybrid perovskites, the big one being that you don't want to introduce water to these materials. So we had to find a new matrix. And in finding the new matrix, because of all the work we've done with the polymer films, we knew what the functions of that matrix needed to be. We need something with multiple OH bonds, at least more than one, and we need something that has a low vapor pressure, again, to protect the integrity of the target during the vacuum process. So what we figured out was that we could make co-solvents for our solutions. So basically you have a primary solvent for the perovskite, something like dimethyl sulfoxide, DMSO, which is typically used for these materials. And then we use polyalcohols for the matrix. So something like monoethylene glycol, it has more than one OH bond, it has a low vapor pressure, and works very well for the maple process. So this is sort of showing what we have for the polymers. You have these emulsions, these emulsified particles get transferred to the substrate, and then as the emulsified particles build up on the substrate, that's what determines the properties of your film, right? The size and shape of the emulsified particle determines how well they can pack in the film and what the order will be in. This is a cross-sectional scanning electron microscope image where you can actually see those emulsified particles. In contrast, for the hybrid perovskites, we have solutions. And those solutions are frozen, and when we deposit the film, we're actually delivering the organic and inorganic precursors to the substrate, which then form this three-dimensional structure, this crystal structure, either during the deposition itself or with additional annealing to form the crystal. So this gives a lot of benefits for these hybrid perovskites. One, we can control the film composition and the thickness in a vapor-based process, which can be difficult to control because of the organic molecule that's very sensitive to any type of thermal evaporation. It's a gentle deposition technique, so you're not going to damage that organic material. You can actually have very low solubility solutions and still get reasonable film thicknesses with maple. And that's important because often, especially when you go to the larger organic molecules, it can be difficult to have the inorganic and the organic part in a single solution. But because maple can have a much lower solubility for that solution, you can still sometimes get them in a single solution together. And again, it can enable heterostructures of these films, even though they might have the same solubility. So just as a demonstration, we have shown, and this is all work done in collaboration with David Mitzies at Duke University, we've shown solar cells made by the maple process. So you can see the morphology from an SEM image that's very typical from what you would get from spin coating these, as well as the X-ray diffraction patterns that demonstrate the presence of this crystal. So we made a device heterostructure for a solar cell where just the active region of the hybrid perovskite was deposited by maple, and we made solar cells, and this is the demonstration of the maple. So this data is a little bit outdated, but at the time that this was demonstrated, you can see that this maple film that we didn't spend a whole lot of time optimizing was still giving us device efficiencies very comparable to other approaches for vapor process perovskite solar cells. and we got a stabilized power conversion efficiency of 12.2%. But again, that's not really the interesting problem. The more interesting problem is when we start to take that small organic molecule and replace it with a larger one. So this is showing examples of one of these large organic molecules that can interrupt that 3D framework and give you a self-assembled quantum well of organic and inorganic layers. These are made up of different numbers of thiophene rings in this large molecule. And so then we have the metal halide octahedra, and they can have different metal halides. So it could be chloride, bromide, or iodide. And what's interesting here is that as you change what the metal halide is, you change the band structure. And as you change the number of thiophene rings in this material, you change the band structure. But what's really interesting is what you see here, where when you look at the relative positions of the band structure for the organic part and the band structure for the inorganic part, there's a crossover here, which basically means that by controlling the halide that you choose and controlling the size of the organic molecule, you can get different types of self-assembly of quantum wells for that energy band lineup. So you could have a type 1 lineup where recombination would happen across the organic. You could have a type 1 lineup where recombination happens across the inorganic. Or you could have type 2 lineups where you'd expect to see recombination suppressed because you're actually separating electrons and holes across these two different materials. So this had been predicted. This was expected to happen from early work that David Mitzi had done, but they were not able to demonstrate this for the wide range of organic molecules because they couldn't synthesize the films. And so this is where the MAPLE was really able to contribute to this because we were able to grow different combinations of these large molecules and the metal halides, deposit thin films of these materials. So here we're looking at AFM images and then SEM images of these materials, as well as the X-ray diffraction spectra that match what you would expect for a bulk crystal. And here we can see that in this film, you'd expect to have recombination across the organic. And in fact, that's what we see because we're comparing the luminescence from the perovskite to the luminescence of just the organic part, and it's the same. And in this material, we expect it to have recombination across the inorganic, which is what we see because we get this green color from the perovskite, but the blue color from the organic part. And that's because the recombination in this case is happening across the inorganic. And then for this material, we expect to see no recombination because it's a type 2 lineup. And in fact, it's what we see from the film, the suppression of luminescence. And so this is the type of capability that's enabled by MAPLE, especially with these more complex perovskites that use organic molecules. And so we're working now on an EFRC, an Energy Frontiers Research Center, sponsored by the Department of Energy and led by NREL, National Renewable Energy Lab. And so this is my collaborator, David Mitzi. There's me and my student. This is one of my students, Niera, and my other student, Tomas, is in here right there. So working on this project and doing all of that work related to the perovskite. So that's certainly the research part. When you talk about teaching the things that I teach, so I teach a course on Introduction to Microelectronic Devices and Circuits in electrical engineering. I teach an undergraduate course on solar cells, and of course the most fun course for me to teach is quantum mechanics. And that's really because I struggled with it so much myself that I always get a lot of satisfaction in trying to make it more accessible to students when I teach it and to try to make it not so scary at first when you're studying quantum mechanics for the first time. And so then just to end, I want to talk some about the work that I do related to service, because this is another really important part. So, you're thinking about that intersection of teaching and outreach, and I've really tried teaching and service, and I've really tried to accomplish that outreach with a Saturday Academy that I offer at Duke University. I've been doing it every year since 2014. And so it's called the Student Engineers Network Strengthening Opportunities in Research, or SENSOR Saturday Academy. This is a program for 8th and 9th graders in the Durham Public School System here in North Carolina. And really the goal of it is just to get students on a university campus to expose them to what college life is like as much as possible and to introduce them to the idea of doing research as a career. And so this is one of the classes that came through the system, and all the people in the orange certs are either myself or the staff, which are graduate students that attend Duke. So we bring in a new set of 8th graders each year. From those 8th graders, we invite some of them to come back in their 9th grade year So they're on campus for 12 Saturdays throughout the year, and then we take a field trip at the end of the year. So it's the same group of students that come to campus basically every 2 weeks or so, more or less, spending time on campus and learning different things. What they're studying is basically the context. The reason it's called sensor is to align with the 8th grade science curriculum. We teach them about sensors that are used to evaluate water quality. So we really try to teach them how the sensors actually work. So that brings it into my research area a little bit, thinking about how do you design a sensor, what's the physical mechanism by which it works. But they also learn about the engineering design process, different types of engineers, nanotechnology, and we do some math reviews in the context of these sensors that we're learning. So it's really comprehensive to try to hit on a lot of different topics, but really just to provide a positive experience on a college campus with other students like them that are also interested in science and engineering. So like I said, we have them there. It's a real time investment for the students and their families. They're there from about 9:30 a.m. until 2 p.m. in the afternoon. We serve breakfast and lunch. And they're basically in a lecture and then doing some type of lab experiment. And then at the end of the day, we have different enrichment activities like taking a tour of the campus or going to visit different labs on campus. And again, this is the staff, and for one particular year, so these are the graduate students that work with the program. And so it's nice because it's a learning experience for them as well. They get to work with a small group of students consistently throughout the year and work on their own ways that they think about conveying information and helping to explain difficult concepts. And so it has had some success that we can measure already. So one thing, so we've had about 116 total participants since I did a pilot program in 2007 and then offered every year since 2014. And, we measure their attitudes about STEM before and after the Saturday Academy. So one thing that's really interesting to observe is that their attitudes about science don't change a lot because, these students are pretty much self-selected. They have some interest in science and engineering, or at least their parents have some interest in science and engineering. But one thing that does change are ideas about critical thinking. And so we can see an actual positive trend in their ideas about, certainty and tolerance of ideas, critical thinking, and how they feel about science. And then also, the things that we want them to learn in the Saturday Academy, they're learning some of it. And again, that's not the main goal, that they retain the content, but that they are learning something during this as well. So yes, this is a picture from one of our field trips that we took. And I will just end it there and take any questions.
Oh, thank you very much. So, Herb Winful here. How about one question for your DBR made with the polymers? What's limiting the reflectivity? And how might you improve reflectivities?
Yeah, I think probably the biggest issue is that the interface, because so all of the films by Maple have an inherent roughness. We can get it to about 10 nanometers or less. But that surface roughness means then that when you're having reflection off the multiple surfaces, that it's not going to match exactly what's predicted, and it's not going to behave as well as it should. So my first guess is that it's the fact that the films are not atomically smooth, and so that's reducing the reflectivity overall. And to improve that, I'm not sure there's much we can do to improve that by Maple. As I mentioned, the mechanism by which it works, you have these emulsified particles that are delivered to the film. There will always be some roughness associated with the film. You can try to control the chemistry and understand the chemistry to try to get those emulsified particles as small as possible. And we have efforts in trying to do that, but that is sort of a limiting factor.
Okay. And another question related to teaching now. You said you try to make quantum mechanics more accessible, not so threatening. What particular techniques have you found to be helpful in that?
Right. So I think one thing is that I don't start with the math. I start with the experiments that helped it be observed. So I try to have everything grounded in real life as much as possible. That these are things that are observed and people didn't know what was going on and it didn't make any sense. I don't start with the math because, at least from my own experience, quantum mechanics, the first time I saw it, was presented as though all of this should be obvious and this math should all make sense and this should all map onto your experiences, when of course none of it does. So really just try to make it clear to them that if it seems strange and it doesn't make sense, that's because it's strange and it doesn't make sense. And to just trust me, and then eventually it will start to get better.
Okay. Any other questions?
Hi, this is Becky. I've got a question for you.
Yes.
Okay, my question was, I know in inorganic PLD, there's a lot of work in trying to make spatially segregated targets or to control the rastering such that you get combinatorial deposition so that you can alloy materials and get a gradient of the alloy over space or different gradients vertically within the film. Is that a concept that's been explored within the MAPLE framework as well?
Yes, I didn't spend a lot of time on that. So not so much the combinatorial, where, you know, the idea that I'm going to do all of these random combinations and get like a span of different compositions across a single substrate, but we are able to control the composition. So I didn't get into it, but this is our target cup and it's been partitioned. So we just have the single target cup, but here there are two different emulsions of two different materials. So as you're able to see my arrow, right?
Yep.
Okay, so as the target cup rotates, the laser's rastering back and forth like this. And per laser pulse, you're getting a scattering of those emulsified particles across the substrate. That's what leads to the nanoscale blending of films. So what that means is that the composition of the target cup gets transferred to the substrate. And so we call this the pi partition. So we've done things where we're varying, from 25, 50, 75% compositions by controlling the composition of the target cup. So another development that we've done that actually I've patented is what we call the donut configuration. So there we have an inner circle and an outer annulus, and they have the two different materials there. And the reason that's important is by controlling the raster pattern and the dwell time, you can control the composition. So we've actually demonstrated things like a gradient composition because we can control the dwell time inside and outside the cup, so we have complete flexibility in what the composition is of the film.
Great, and I guess specific with the emulsion and the frozen emulsion approach, which I don't know very much about, but it's been wonderful to learn more about it. I'm just wondering, are there challenges in different deposition rates of the different materials that you're using that make this type of, alloying or mixed approach challenging in your particular configuration?
Right. So, you can have different growth rates, and so you have to account for that. So, for example, you might change the dwell time to account for the different deposition rate, or you might change the concentration of the solution to account for the different deposition rate. So you do have to calibrate, and you do have to understand what that is, but there are multiple ways that you can be certain of what the composition is that actually makes it to the film.
Great. Really fun to learn more about your work. Thank you.
Thanks.
Any other questions? Okay, well, let's thank Adrienne for wonderful talk, and we hope that next time we'll be able to bring you here physically so you can inspire more of our students to follow your path.
Yes, thank you. And I appreciate the effort to try to make the remote seminar work. So thank you.
All right. Okay. So stay well, be safe, and we'll see you
too.
next time. Okay.
Yeah,
Bye-bye.
Bye. Thank you.